All right. Well, today we have our special guest from the virtual world of iTunes U. Right. The people who normally are not here or have not been here usually because they've been taking advantage of the video of the lecture on video are here today. So anyway, that's good. All right. Now I'm giving back some homework. And I also this time on the blue papers are the solutions. So I thought it would be good because there were a lot of questions on this assignment, and so I just went ahead and ran off the solutions for you there, so you can check what the corrections were. So. And then today we have another assignment due, and today we're starting the assignment on sets, right? Chapter 11. So are there, is this going to be another one of those things where nobody has tried the homework and so you don't have any questions?
I have done it. I have a question.
Okay, good. What's your question?
On F.
On 11, is this 11.1F?
Yes.
Okay, so on 11.1F.
You're trying to say the set of prime numbers between 10 and 30.
The set of prime numbers between 10 and 30. Yeah, now, does that mean including 10 and including 30?
I said
Well,
it didn't.
I guess it doesn't matter because they're not prime anyway.
Right. It's like between. But when in your range, you say 10 is, x is greater than 10 and less than 30. And you have to say, and it's prime
Yeah.
in the range.
Yeah.
Okay. And then the body.
So the question is, do you have to use that the prime predicate, right?
No, I don't know if you could use it in the body.
Well, I mean, there's always, oh, I see. Yes, it has to be in the range. Okay. The range is always the Boolean. Mm-hmm. Yeah. Okay. Yeah, so to use prime, and did they explain what, I don't think we did the prime.
They just said
use prime dot x, but you understand what prime dot, so prime dot 13 equals true, right? Because 13 is a prime number, and prime dot 14 equals false. And what's the definition of a predicate? Function that returns type Boolean, and that's what prime is. It's a predicate. It returns type Boolean. It returns true or false, depending on whether that's a prime number. Okay?
Are we allowed to use that then?
Yes. It would be an interesting exercise, wouldn't it, to define prime as using a quantification. You might think about that. That would be an interesting. I think we could do it because we already know what it means to be. We already have a definition of divisible or divides. So you would use divides, and then you would have to expand out divides. That might be an interesting thing for you to look at.
And you can use quantifications within the range?
Sure, as long as they are Boolean. Yeah.
And then for 11.3.
11.3.
Do you want us to prove it just like a normal proof?
Yes, 11.3, you're supposed to prove that. So here, 11.3, you're supposed to prove B, the set BB equals the set B. And what I recommend that you do is, I recommend that you start with the left-hand side.
What terms are we allowed to use?
Well, here they are.
All of them?
Well, I think the only thing you need is 11.2.
All right.
Because what is this? Is this set enumeration or is this set comprehension?
Enumeration.
This is set enumeration. I recommend you start with the left-hand side, use set enumeration, get it to comprehension, do some manipulation, then get it back to set enumeration, and you should be able to get that. I mean, you could almost do this in your head, I think. Right? I mean, did you just do it in your head?
Yeah,
Well, I mean, look, what is enumeration? What is E0, blah, blah, blah? You know, what is the set
Yeah.
BB? It's the set of all x such that da 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 da, and then da da da. And x equals, yeah. Are we good? Is everybody, any more questions?
I have a general question.
Sure. General
I
question?
watched the video this time.
Yeah.
And when you're like giving like examples, I was confused to how like normally like with the set comprehension you have the dummy and then the range is always like a typical range would be like 0 less than or equal to x less than 5 or something.
Yeah, but it can be
But
anything.
but you're using this, and then you have a body which is some expression.
Yes, you have a body. Yes, and then so the range is always a Boolean, and then you have a body, and that body has some type, and it can be any type.
Yeah, and that body is normally an expression using x, like 2 times x or something. But then with your, when you like skip back to and you start defining set comprehension, you have the dummy, and then you have a range where it's like x equals a or x equals b, and then body just x.
Yeah.
But that x doesn't have an expression or anything.
Well, x is an expression. What's the definition of an expression? What's the definition of it? It's either what? What's the first part of? Well, wait. What's the first part of the definition of an expression? It's either a what or a what? It's either a constant or a variable.
Okay, so
And then if he is an expression, then
Yeah.
parentheses. So that's
So
that's a variable. So
does
that's
x just have to be like just a variable, or can it be like?
it can be
2
any
times
expression.
x?
yes, it can be any expression.
Okay, so that's what was throwing me off.
Yeah.
So it's not just a variable x.
It can be any expression. And the examples that we gave last time, we had examples like we had 2 times I, we had x to the y.
Normally when you say like an expression for the body, like normally we have like range p or like
Mhm.
body p, and that's like the capital denotes
Yeah,
the
yeah.
expression.
Yeah,
the
yeah.
T of lowercase.
Yeah, okay, now that's
We
you.
kind of gave you the idea that it was just a variable.
No, you're right. That's actually a good point. Now,
Why don't we write it like body e this?
yeah, okay. Now that's a very good point about the notation. Now, when we were doing propositional and predicate calculus, we made a big deal out of the fact that lowercase was a variable and uppercase was an expression. But now we're not just doing propositional and predicate calculus. We are applying it to a theory of sets. And so now because we're in a different problem area, the convention is going to be slightly different. Starting with this chapter, uppercase letters are going to represent sets. They're going to be variables, and they're going to represent sets. So that might be what's throwing you off a little bit.
That's exactly what's there.
You see what I'm saying? So you just be aware of that.
Got it.
Yeah.
So uppercase letters are no longer.
Are no longer just expressions. Yeah. Now now we're in the context of we're applying this to in another field, in another area, and so now, yeah. So now, and in particular in this chapter, capital S, capital T, capital U, capital V, those are going to be set. Those will be type sets frequently.
Got it.
All right. Everybody got everything all cleared up now? Okay. So let's continue on then with our theory of sets. All right. So what we know now the difference between set enumeration and set comprehension. Now the next axiom, 11.3, is called set membership. All right. Now set membership defines, so this is 11.3. It formally defines this is an element of, okay? So it's basically an element of, okay? And this is called set membership. And the structure is like this. E is an element of S. Now, actually, here's the first example of having uppercase be not an expression, but be a set. Well, S actually, I kind of take that back. S actually, it can be an expression, because what we're going to find out is that sets have operators on them too. So S can represent any set, but it actually could be an expression that represents a set.
Is a set a type of expression?
No, a set is,
It's a subset of expression.
well, 11.2 shows two ways to write a set. Okay, you can write a set as a set enumeration, or you can write it as set comprehension. So this S could be written either one of those two ways, but there are also operations on sets. So have you ever heard? We're going to investigate these. Have you ever heard of the union of a set or the intersection of two sets?
Yeah.
Okay, so this could be the intersection of two sets, the union of two sets, whatever. Okay, so, but anyway, for our purposes right now, the definition of this is an element of. Here's how this works. Now, see if we can get this. This E is called an element. Okay? And this S is a set expression. All right? And furthermore, this set membership expression is Boolean. In other words, either E is an element of the set. In other words, either that's true, or E is not, or E is an element of S is false. Are you with me? So this is either true or false, okay? So now, this element of, now here's something that's interesting about this element of. This element of is one of the few functions that does not have the same type for both its arguments. Element is one of the few functions that does not have the same type for both arguments. Are you with me? Now, do you remember whenever we said equals? Suppose you say x equals y. Now, if you consider equals to be a function of two variables, what is the type of the equals function? Do you remember that? I think I asked you this on a previous exam. But what? But if it, but hold on. Here, if you say x equals y, well, if you consider this to be a function, then it would be the function, and you wrote it out like it in function notation. It would be like equals x y. So if x and y have type t, what is the type of this whole function? T cross t arrow Boolean. Are you with me? And remember, so this and this have to have the same type. Well, what if you consider this to be a function? Are you with me? So if we would consider this to be a function, we'd have to give it a name. Like here we have to give this symbol the name equals. Well, let's just say that we give this, like element of. All right. So let's give this the name element of. So if you said. You
can do like an integer as an element of reals.
So if you called this. No. So if you say, sorry. So if we say element of ES, then what is the type of this? What is the type of this in the same way that equals has type T cross T arrow Boolean? What would the type of element of be?
T sub E.
Well, yeah. Suppose E has type T. Suppose E has type T. It would be T. If E has type T, it would be T cross what?
Type of S.
But what is the type of S?
Set.
Set what? Oh, we did that. We did this before. Set what? Set what? Huh? Do you remember what we said about? Look back in your notes. What did we say about sets? What did we say about the type? So this would be T cross set T, right? And then what?
Arrow B.
Arrow Boolean. It still returns Boolean. Are you with me? So what's interesting is that with equals, this has to have the same type as this, but this is not. This is T, this is type set T, arrow Boolean.
Equals, couldn't you have like an integer and a positive number or something?
No,
I mean, they'd be two different types.
no, okay, okay.
Okay.
To do this in computing, you would have to typecast one of them to the other.
Oh, okay.
So, I mean, so the answer is no. You know,
The computer would get.
the compute, yeah,
Okay.
yeah. So, I mean, if you think of it from an operational, I mean, what we apply this theory to is they have to be compatible types. All right. So does everybody understand what's going on here? Okay. All right. So now here, let's do an example. Let's do an example of 11.3. Okay, so just to make it concrete a little bit, let's say, now what do you think this is? 2 is an element of the set I, range 0 less than I less than 4, body I. All right, so here we have, what does it mean? What does it mean for 2 to be well, I'm not asking you, yeah, this happens to be true, right? But because how did you know that it was true? In your head you worked out what, the possible values of I here are what?
1, 2, 3.
1, 2, 3, so, and it's I, the set body I. So it's the set 1, 2, 3, and 2 is an element of the set 1, 2, 3. But that's not the point. The point here of 11.3 says this equivales. What is the meaning that 2 is an element of this set? What does it mean for that to be? What does it mean? It means what?
There exists
It means there exists a what?
an I.
Yeah. Only we better use a different variable because this is a dummy variable, right? We can use any dummy we want, right? So there exists an X. Actually, there it is. Exists an X, range what?
Same range.
0 less than I less than 4.
Less than X.
Oh, yeah. Well, okay.
They use the same
They
variable.
use the same.
You can use
Okay.
Yeah, you can't. It doesn't matter.
0 less than X less than 4, such that, and body what? According to this, body what?
X equals.
Well, body what? F is the one.
2 equals X.
Okay, so 2 equals X. All right? So now look, you guys, once we have this is equivalent to this. Once we get it on to this, what do we have to work with?
everything.
All those theorems and axioms for existential quantification. We can do trading, we can do da-da-da, we can do existential double trading, we can,
Golden rule.
that's our, exactly. This is it, sports fans.
Except we have 3 more.
This, well, I mean, providing X does not occur in F. Yeah, yeah.
Well, I saw it.
We have a full class.
Now, so does everybody understand what this means then? This is the meaning. This is why. This is what it means for 2 to be an element of this set. And this is set comprehension, right? Okay, so for 2 to be an element of this set, what it means is there exists an X, 0 less than X less than 4, 2 equals X. Or we could have said there exists an I, 0 less than I less than 4, 2 equals I. Actually,
Yeah.
That's what they do.
yeah.
It doesn't really matter.
It doesn't matter because it's a dummy, but actually I think I like I better. But either way, it's fine. Because we all know how all these quantifications are used, right? Okay, so that's an axiom. That's the meaning of there is an element of. Now, how about 11.4? Let's take a look at 11.
Axiom universe. That's like a superhuman name.
Yeah. Okay, axiom. Now this axiom, extensionality. Now what do we have on the left-hand side of the equivalence in 11.4?
An expression.
An expression. What is that expression on the left-hand side of the equivalence? S equals T. So, well, no. Did you say subset? No.
Set equals set.
Yeah, what we have is one set equaling another set. All right? So now, whereas 11.3 was the definition of what it meant for something to be an element of a set, an object to be an element of a set. 11.4 says what it means for two sets to be equal.
So I mean they have the same elements?
Yes, it means they have the same elements. But by definition, for one set to equal another set, what it says is what? It says for all x, range true, for all of them, it says x is an element of S. Oh, hold up, what does element mean? Oh, that's 11.3. Are you with me? Ah. Okay, it means x is an element of S equivales x is an element of T.
So if one's true, the other has to be true.
If one's true, the other one has to be true. If one's false, the other one has to be false. All right, are you with me? That's the definition of what it means for two sets to be equal.
Okay.
All right? So, 11.4 is used to prove two sets are equal.
Extensionality.
Used to prove two sets are equal. And, doesn't that make sense? I mean, by definition, if x is one, and then it has to be in the other. If it's not in the first, it can't be in the second. Right? So that's by a mutual implication. Right? The equivalence, you remember mutual implication for equivalence? P equivals Q equivals what?
R.
No. Mutual implication.
Q and P follows from Q.
Yeah, P implies Q and Q implies P. Right? If P, then Q. Are you with me? Okay. So 11.4 is used to prove two sets are equal. Okay, so to show that S equals T, what you do is you prove that for all x, range true, x is an element of S, equivales x is an element of T. That's the recipe for proving. So the main thing is that, and furthermore, this is also, 11.3 is an existential quantification. 11.4 is a universal quantification. So 11.3 and 11.4 relate all of set theory back to predicate calculus. So 11.3 and 11.4, 11.3 and 11.4 relate all set theory back to predicate calculus. Relate all set theory back to predicate calculus. Okay, so that's the big deal. Okay, so now with these two things in mind, with these two sets in mind, what we have now, what we're going to explore now are, we're going to explore some special sets. Now, unfortunately, our author doesn't define these. He defines some of them in footnotes, and he doesn't give them numbers or anything. So I found it helpful to formally define these special sets. And the first set, we actually gave an example of this first set last time, I think, at the end of class. 11.4.1 is the empty set. Okay, so first one is called the empty set.
Yeah, we did do this the very last.
I think the very last one was an example of the empty set. So the definition of the empty set, it has a very simple definition. And the empty set is denoted by a 0 with a slash through it. Okay? so actually, let's say this. There's two ways to write it, actually. Two ways to write empty set. The two ways are a 0 with a slash through it, or sometimes we write the set, we write it like set enumeration, but we don't put anything in the, we don't put anything in it.
We can't write what the axiom says to write?
Well, no, the axiom uses this notation.
But it also uses
What?
x is false.
Well, yeah. And that's what it is. What the empty set by definition is, 11.4.1, it says the empty set is x, range false, and furthermore, the body can be anything. It doesn't matter because the range is false. So it's not going to have anything in it regardless of what the expression is. So the expression E is irrelevant. But that's the definition of the empty set. Okay? Now, 11.4.2 is an interesting property of the empty set. It says E is an element of the empty set, equivales false. Seems obvious. Is it an axiom?
No.
So can we prove it? Yes. And will you prove it in your homework for next time?
Maybe.
Yes. When you come back from Thanksgiving vacation, you'll have that for me on Monday. Or if you want to not have anything hanging over your head when you're eating that turkey, you can do it before you go home or wherever you're going for Thanksgiving. Right? So, okay, so anyway, 11.4.2 is membership in the empty set, and that's a homework problem. All right, now there's another one that's not up here, but I want to state it anyway. It's the singleton set, empty set. The next one is,
Does that mean there's only one thing in it?
yeah.
Okay.
The singleton set is the set with one element. No, it's not up there.
11.4.11.
Okay, the singleton set is the set with one element. And by 11.2, it can be written two ways. By 11.2, it can be written two ways. You could either write it enumerated, like, it's the set with one element in it, or how would you write this with set comprehension? So now, using 11.2, how would you write this set comprehension? It'd be the what?
X.
Yes, okay, the set over X, range what? X equals E,
No.
body what? Body X. Now, is everybody clear on how to do that? How we get this from 11.2? 11.2, it has an arbitrary number of elements, but if there's just one of them, then, okay? Are we good? Okay, so this is enumeration. Okay, so this is enumeration. And this is comprehension. Yeah? All right. Now, let's go through. Now, I think we have enough, before we go on to the universe, I think we have enough under our belts here to where we can start proving some interesting set theorems. So this time we'll go around the room. Who wants to start? So here's a theorem. I'm just a trivial one that's not on the equation sheet. So here's a theorem. E is an element of the set with E.
True.
Well, it is true. But how can we prove it?
Axiom 3.
So how are we going to prove? So here's a theorem. So what's the proof? Well, I know, but how do we? So what should we start with?
11.3.
Well, what should I write down first? What should I write down first?
Whole thing.
Write down the whole thing.
Whole thing.
Yes, let's write down the whole thing. So E is an element of set E. Okay, so who wants to go first? We'll go around the room.
11.3.
Kyle?
I want to go first.
All right. E is an element of set E. Equals by what? You just give us the hint. Give us equals by what?
11.3.
I disagree.
Set membership.
I would say 11.2 and change the E. from
Okay, so Ben says 11.2. Okay, so Kale,
Fine.
if Ben says 11.2, so they're using 11.2, what is this?
E sensitive.
He's using 11.2 on this.
Yeah.
So what would it be?
X, range X.
Hold on, what's the first thing I write down? You have to, E is an element of
X, range X.
a set, we say, the way we say it is set over X, range what?
X equals E.
X equal, hey, Kale, you're not Kale. X equals E, body,
X.
X. Actually, now it's your turn. Okay, so are we good? Okay, so now what do you think we should use?
11.3.
Oh, shh. So now you claim we should use 11.3?
Sure do.
Okay, Ashley, she says 11.3. What happens if we use 11.3 on this?
We get there exists an X.
So we get there exists an X,
Range
range,
X equals E.
X equals E. Is everybody following this?
Body
Body,
E equals X.
E equals X. Is everybody clear on this? Okay, so Josh, what do you think? What should jump out at you here from predicate calculus, all of our predicate calculus stuff? What should jump out at you right here?
It's jumping.
It's been a while. It's been a while.
It's been a while. Predicate, yeah, dust off those, will get your equation sheet out.
Yeah.
Now what should just really, once you see it, you think,
Wait,
oh,
how did
it's the
Can we
rule.
prove that like P or like range body equals true? We can prove that.
No,
That should be a theorem.
no.
That should be there.
It's like the 1.7.
You can't just make up a theorem.
That's lemma is.
Equals by Josh's theorem.
Yeah.
That's what a lemma is.
Josh's.
If we can prove it.
Yeah, we can.
No. Come on.
The 1 point rule.
How is that supposed to jump out at me?
Because anytime you see an equals in the range,
Yeah, it should
boom, that should jump out at you. And what is the, okay, so tell me, did you look it up?
that next time
Okay, so this equals by the what? 1 point rule, which is what? Give me a number.
5.
Josh? Man, everybody's named Josh. 1 point rule, which is what number? Not what number?
8.14.
8.14. Okay, 1 point rule equals, okay, Rochelle, Rochelle, equals by the 1 point rule. How do you apply the 1 point rule to this? Okay, so look up 8.14, right? So it's E equals X, yes, so that's E equals X, and then with what? Textual substitution, X replaced by E is right. And so this equals, Mason, this equals by textual substitution, what? How? Mason, all right. Equals by textual substitution what? E equals E, which equals, okay, now it's your chance. Equals by 3.5, which is what?
Reflexivity.
Reflexivity. 3.5. Reflexivity.
Which is?
True. Oh, we could have just said, yeah, we could have said which is.
3.5.
Well, we could have said which is
Say
3.5.
Which is 3.5.
Okay, we'll do it that way.
Which is.
No, it's totally more true.
It's 3.3.
Yeah, which is
Oh,
3.3.
Oh, this is 3.3.
No, that's 3.5.
Okay, which is,
3.3 is E equals E equals.
okay, which is 3.5. Boom.
Boom.
Now look, you guys, look how much everything is built on what went before.
That's like the first day.
Look, I mean, yeah, all the way back to 3.5 and in APA, the 1-point rule. Okay, and then we see how everything follows. Is that cool? So you see how to do these set proofs.
Cool.
Well, I'd say it's pretty neat.
It's pretty cool, I suppose.
I don't sound like that.
All right.
I know you don't sound
Now,
Can we prove the universe now?
no, not yet.
Oh, it's an axiom. You can't prove it.
Right. Okay. We'll talk about it in a minute.
Proved universe.
Dang it. Josh, I wish you sounded more like a flight accomplished.
Okay, now let me ask you this. Let me ask your opinion about something. What do you think about this? E equals set E. What do you think? What do you think about this expression?
Duh.
Is it true?
Yeah. No. They're not equal. Different type. Yeah.
This is not a valid expression. Why not? It's not, yes, not a valid expression. Well, we won't write down the, I don't think we'll put that on the board. And why is it not a valid expression? What's conflicting?
The types.
Okay, we have a type conflict. Why do we have a type conflict?
They're different.
Because E and this set E are not the same type.
Their types are mapped to each other.
Okay, so if E were an integer, then what would be the type of this? If E were an integer, what would be the type of this? It would be set integer. Yeah, set parentheses integer. Are you with me? Okay, so they're not the same type. All right, let's prove another one. Here's an interesting. Who was last? Okay, Ben, it's your turn. Here's a theorem. The set 1, 3 equals the set 3, 1.
I would say that that's true.
I would say it's true, but let's prove it. So you want to start with the left side to get it to the right? Or
Why don't we use letters? Let's have like A, B equals B, A.
what? Sometimes we do one, sometimes we do the
I'll do
other.
the left side.
Okay, so 1, 3. Okay, so Ben, what do you think we should do? 1, 3 equals by what?
I think we should change it from enumeration using 11.2.
All right, using 11.2. So Kale, if we use 11.2, what's this?
The set of
It'd be set over
X,
X,
range,
range,
X equals 1 for X equals 3,
body,
X.
X. Okay. Elizabeth, now what do you think we should do? Because we're trying to prove that this, so now what do you think we should do? Here we have this, and we're trying to prove this is this. So what do you think we should do? Yeah. Oh, no. Is that the name of it? Wait, look up. Do you have your equation sheet? Wait, hold on.
Do I need like the exact number?
Well, I mean, either the number or the name, but I don't think, I think reflexivity is y equals y. Hmm?
Symmetry of or 3.24.
Yes. Okay, so it's 3 point, so equals by 3.24, symmetry of or.
Uh-oh.
Okay, and that's going to give us, Ashley, so what's that going to give us?
Set of x, range x equals 3 or x equals 1, body x.
Body X. And this is sets, right? Now look, yeah, these are sets, right? And then, so Josh, now what? Obviously.
True.
No, what do you mean true? We're not trying to get this to true. We're trying to get this.
I always know pages. Oh,
Yeah, I know. Okay, so 11.2, and go ahead and tell us what it is by 11.2. Set 3, 1.
Boom.
and boom, we're done. Okay? So what do you think about this theorem? Does everybody see how that theorem worked? So what does that say about sets in general? That if you enumerate them, what does that say in general? You can do what?
You can make move them around.
Yeah, the order doesn't matter, right? What about this? Do you believe this? Suppose we have this theorem. 1, 1, 3 equals the set 1, 3.
Do sets have indexes?
No.
Okay.
Do you believe this? The set 1, 1, 3 equals the set 1, 3.
That's not right.
Yes, yes.
I can make that happen.
I don't think we need to go through all the details, but how would you make it?
1 over
It's just
1
like
is 1.
the b comma b equals b. Because
So
you're
11.3.
Oh, you already did that. You already did one for me. Yeah. So it follows from, so what does that follow from? I mean, what,
Isn't that P or P is P?
yeah, and what property is that? P or P equals P. What property is that?
idempotency.
That's idempotency.
Yeah.
So the proof follows from the idempotency property of OR. We won't do it.
We did the same thing we just did, but
Yes. Proof follows from idempotency of OR, okay? Which is P or P equals P. Okay? All right, now another special set.
special set. Is it a couple set?
Special set continued. Okay? The next special set that we're going to look at is the universe. Okay? So this is 11.4.3. It's called the universe. So that's 11.4.3. And by definition, the universe.
Is everything.
Now, here's the. Unfortunately, there's a problem. Yeah, it is everything. Unfortunately, we have a problem here. Because later on in the chapter, our author uses S and T and U and V to be just general sets. And if you don't write it, if you're not careful with the way you write it, it's not clear whether U is the universe or whether it's just some arbitrary set.
So that's gonna be bold.
So it has to be some kind of bold. So I don't know how do you, maybe we can put a line, maybe put a line here.
Just make it really bold.
Or maybe we should put, maybe we should do
Put a U
this.
inside it. Yeah. Do that.
I get a W.
Put a bar over it or something.
Put a U inside the U.
Make it
Make a U bar.
rebar.
Like that?
That's universe.
Nah.
Makes it more like a tab, though.
Well, we need to figure something out.
U with the bar over it.
Yeah, U bar.
You mean like this?
U bar.
U bar.
The average of
Yeah, that doesn't mean,
Then how about?
okay, I'm going to do it like this.
Let's put an umlaut over it.
That doesn't even look any different.
That's the two.
Well, it has an extra thing here.
The indices.
Because I think in the book he makes this bold here like this.
He does make the left side bold.
Yeah, so we'll do that. Okay, so here's U. Okay, so anyway, this the universal set. Now check this out. It's the set of X. It's a set over X. Range what?
True.
True. Body X.
Every X
That's every X. All right.
is a giraffe and X.
Now, here's the thing, though, that you have to be aware of. However big, the elements that are in this set depend on what? They depend on the what?
Type.
On the type of X, okay? So U depends on the type of X. The universal set depends on the type of X, all right? So actually the way to write this with all the types is you would say U, and then we would annotate this with type set T, and that would equal the set over X, and we would annotate this X with type T. Are you with me? Range true, body X. So this is the fully annotated. Does everybody understand that this is the same thing as this, but we've just shown what the type of U is, and we've shown what the type of T is? Are you with me on that? Okay. So the definition of U depends on, I mean, like, if X are the natural numbers, then this is a set of numbers, then that's the set 0, 1, 2, 3, 4, 5, 6, 7, 8, all of them, the naturals. If it's the integers, it's negative infinity, blah, 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 all the way up to negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, right? And there's just one more thing that we're going to do, and I'm sure that once you have to use this next fact, you will have forgotten this, and I'll say, remember when we said? And you'll say, I don't remember when we said that. Well, here it is. Here's what you will forget. Dummy renaming with sets. Dummy renaming with sets. Now, you guys, here's the thing. A lot of the stuff that we did before applies to set comprehension, but we're not going to bother to have specific axioms and theorems for these. Yeah, like change of dummy. We can do change of dummy, but it's done exactly the same way, so we're not going to bother to show change of dummy. But here's how it would work. Check this out. Suppose we have the set over X, 0 less than or equal to X less than 5. Body X squared. Right? Are you with me on this? So if X is an integer, then what are the values of X? 0, 1, 2, 3, 4. And so the set of X squareds is 0, 1 squared, 2 squared, 3 squared, 4 squared, right? Okay, that's it. Okay, so now do you have your equation sheets? Look up 8.21. 8.21. Dummy renaming. But what we're going to do here is we're going to say 8.21 for sets. All right? So what does 8.21 say that you can do for a quantification? For a star X, for star X, what does it say you can do? What is it? What is 8. What is 8.
You just change the variable to whatever you want it to be.
Right. So what we'll do is let's change it to Y. So this would be set. So this would be dummy Y. And then according to 8.21 explicitly, what does it say you do?
The range
You do.
X replaced by Y.
Yes. So the range here is 0 is less than or equal to X is less than 5. And then it's going to be like X replaced by Y. Are you with me? Body. And then it's X squared with X replaced by Y. Is everybody clear on that? And then we end this with a set, because this is for sets, not for quantification, right? And so this equals by textual substitution, and we can go ahead and do the textual substitution, and what do we get? Set over Y, 0 is less than or equal to Y, less than 5, body Y squared. So we're not going to bother to write down the version of 8.21 for sets, but you can do dummy renaming.
Can we do any of those universal things? The ones with the stars. Can we do any of those for sets?
Oh, no, you can't do tradings. Oh, well, but the tradings were not general.
Right. The general.
Let me think about that. Can you do any of them? Ooh, that's a good question. Like,
One-point rule,
what-
range split.
no. Even distributivity, no. I guess what I'm saying is this is the one.
Range doesn't even make sense.
Yeah, well, but what you do is you use the way you use those is here again. Here's the connection. The connection is set memory 11.3 and 11.4 is how you get back to that world.
Okay.
But in this one case, I just want to show you that you can do dummy renaming.
Okay.
And that's the way it works. All right, good deal. See you all tomorrow.